As a way to aid NASA's ongoing Artemis program and as a means of fulfilling the objective of the NASA Mines program, our research focuses on the development of a helical anchor-based thermoelectric generator that makes use of the Seebeck effect to generate power from an existing temperature differential. My team investigated the feasibility of these power sources for use in a lunar environment, relying on experimental observation through both in-situ testing with a physically built testing rig as well as supplementary simulations done with CAD modeling through Fusion 360. The final design employs a top-down system of heat dissipation with a modified helical anchor meant to be embedded into lunar soil. This system would be able to act as both structural support and as a solid state and long-term power source without the need for frequent maintenance. So first, let's discuss the properties of the moon itself. The moon has very different properties from what we're used to here on Earth, with surface gravitational acceleration less than a sixth of Earth's, an essentially negligible atmosphere, and abrasive sand-like soil covering its surface. We note especially the latter two, as the lack of a significant atmosphere means that there is essentially no thermal energy on the surface of the moon dissipated through convection into the atmosphere, requiring heat transfer into lunar regolith instead. The surface of the moon's crust can be described with three distinct layers: the dust and soil layers, comprising a region known as the upper lunar regolith, and the bedrock layer. The dust layer is a fine coating of settled soil particles from the surface of the moon to a depth of 2 centimeters. Covering it is the soil layer, a more compact and more stable layer that reaches a depth between 5 and 10 meters. Then is the bedrock layer, which comprises the rest of the moon's crust.
The project takes the natural temperature differential that exists on the moon and applies it to a thermoelectric generator. At the equator of the moon, there exists a 150-degree Kelvin temperature differential between the surface and just 20 centimeters down, where it then stabilizes. It becomes fully stable at 50 centimeters. This is because lunar soil has a varying density and therefore has a varying thermal conductivity. As it gets deeper due to soil pressure, it compacts and then conducts heat better. That means as you go down, heat is better at dissipating and it tends to collect at the surface. We know the temperature differential at the equator is 150 Kelvin because we have data and we expect it's still a very, very large number at the South Pole.
Our design evolved significantly throughout the design phase of the NASA Mines program, undergoing several massive changes until its final form. We began with a device using long-scale wiring that relied on the cold-trap nature of Shackleton Crater and other nearby impact craters in the lunar South Pole region, making design changes later on that reduced its reliance on permanently shadowed areas and abstracted heat transfer to essentially any region on the moon's surface, also significantly reducing the complexity and cost of required installation procedures. TEGs work by way of the Seebeck effect. They utilize an applied temperature differential across its two ends, the hot and cold plates, and the following transfer of thermal energy from the hot side to the cold side, and siphon off a portion of this thermal energy to produce current. The natural temperature differential between the moon's surface and subsurface can be utilized for these TEGs by integrating them with a modified helical anchor system. Helical anchors are a proposed method of structural support for surface-based lunar structures that would otherwise not be able to support themselves in the silty, sand-like nature of lunar regolith. These anchors are essentially long, hollow steel cylinders with helix-shaped plates running along the bottom region of the anchor, much like the threads of a screw or bolt. They are installed with rotor equipment, again, much like the installation of screws or bolts, but on a much larger scale. These anchors can be modified and integrated with TEGs for use on the lunar surface. We can rest our TEG plates inside the hollow interior of the anchor on the surface and sit at the top a custom radiator module made of concentric copper cylinders and, with other design modifications, establish a top-down system of heat transfer that can provide essential power for the Artemis base camp.
The reason we chose to use thermoelectric generators over any other device for this project was because thermoelectric generators provide a steady, renewable source of energy in a solid-state form that can be used to reclaim waste heat from any of the other processes that might be going on the moon at this time. For example, you could take the hot plate of the TEG and given that you can form a good thermal connection with anything hot that is on the moon, you could put the hot plate of the TEG up against, say, a nuclear reactor and use the TEG to reclaim some of the waste heat that would otherwise be going to waste from that reaction and turn it into usable electricity. You could, as long as you have a good connection to the hot side of whatever you're using and a good connection to the moon and the lunar regolith and the cold there, you have the temperature differential that you can use to generate energy with the thermoelectric generator. Another reason that we chose to use TEGs instead of anything else was because another reason that we chose to use TEGs instead of solar panels specifically was that TEGs actually don't need to be cleaned nearly as much as solar panels do. Solar panels you have to wipe off almost every day because they collect dust very easily, and if they don't have a solid, steady exposure to the light of the sun, they will not be producing energy at as nearly as much efficiency as they would otherwise. Thermoelectric generators, on the other hand, only have to be hot, and they will work at their maximum efficiency.
To test our concept and prove the innovativeness of our design, we had to provide reasonable data from experimentation. However, since we did not have access to the lunar surface itself, for obvious reasons, we decided to approximate the lunar environment with an experimental testing rig built entirely from scratch, as well as use computer models that ran simulations with CAD modeling software.
The test rig is a vacuum chamber with surface heating and subsurface cooling systems that simulates a lunar thermal environment for the experimental testing of our mock thermoelectric helical anchor prototype. To simulate the lunar surface's thermodynamic behavior, the experiment was performed in a near vacuum. To achieve this, we made a vacuum chamber with half-inch acrylic sheets. The vacuum chamber is held together with acrylic cement and 16 steel brackets with O-ring sealed bolts and is sealed with silicone. Instead of the planned bolts on top and bottom of the box, a design change was made to make the top of the box easily removable for access to the experiment. The unused holes were sealed with rubber patches and a silicone ring was put on top of the vertical acrylic sheets. Atmospheric pressure pushing in on the rubber box top created an airtight seal. The box top also had the added weight of the sandbags pushing down to squash uneven parts of the silicone ring and create a seal. The vacuum chamber was not perfectly airtight, but it held a near vacuum with the air pump constantly running. To simulate lunar soil, the box was filled with sand to a depth of 75 centimeters. Sand was chosen over other possible simulants, such as sawdust, because of its availability and known thermal properties that are similar to actual lunar soil. To simulate solar radiation, 3 250-watt heat lamps were hung 5 inches above the sand. For the 750-watt test, all 3 heat lamps were used, and for the 500-watt test, only 2 of the heat lamps were used. To simulate the temperature stabilization in actual lunar soil below a depth of 50 centimeters, we used a welding torch cooling system to run water through copper pipes in the soil to maintain a steady temperature. The cooling system was designed to keep the water at room temperature and could remove up to 1500 watts to do so. The water pumped by the cooling system was run through a copper pipe coil embedded in the sand below a depth of 50 centimeters. This system was very effective at keeping the sand at room temperature, our lunar subsurface minimum, and removing all energy added by the heat lamps to create a net zero energy in the test rig. Acrylic is already thermally insulative, but as an added measure, the outside of the box was covered in ceramic fiber insulation. Ceramic fiber and acrylic have similar thermal conductivities, but this added layer tripled the total thickness of insulation between the experiment and outside air. Important locations for the temperature sensors were chosen based on thermal simulations. Because of hardware limitations, we could only use 10 temperature sensors. The temperature sensors were buried at their respective depths as we filled the test rig with sand. To test the concept of using a heat sink inside a helical anchor to cool thermoelectric plates, we designed a mock anchor, a proof of concept model that could be tested in the test rig. The helical anchor was mocked by a steel pipe. For our test, the absence of the helical plates did not affect the performance of the radiator cylinders. Copper was chosen for all components that transferred heat due to its high thermal conductivity. For simplicity in the proof of concept model, The heatsink was designed to have two radiator cylinders, which function similar to radiator fins. They consist of a copper rod and copper pipe. The heat transfer block, or HTB, was a cylindrical copper block. For our test, the HTB was sized to have the thermoelectric plates at ground level, but having the HTB as a separate component from the radiator cylinders allows the thermoelectric plates to reach a heat source at any height above the surface by changing the height of the HTB. Constructing the mock helical anchor without the ability to weld was very difficult. We originally tried soldering the copper, but the pieces were too large to get to a high enough temperature with the available blowtorch. Metal brackets instead were used to attach the HTB and inner copper rod, which then rested atop the outer copper pipe in the test rig. All of this rested inside the steel pipe. We were very careful to fill the gap between the outer copper pipe and steel pipe with sand, as if it had been drilled into the ground. Thermal paste was used to ensure full heat transfer on all joints. The original design used aerogel to insulate the HTB in radiator cylinders above 20 centimeters, the depth where temperature stabilization starts. However, due to shipping delays, we used ceramic fiber which was readily available. Ceramic fiber was installed in two pieces, a thin outer ring between the copper components and steel pipe, and a thick blanket on top that shielded the exposed areas of the HTB from the heat lamps. We used 4 commercially sold thermoelectric units. Circular thermoelectric plates would have been ideal, but were not available. They were connected in series, and their voltage over a known resistance was measured to determine power output. To predict the results of the experiment, we ran a thermal simulation in Fusion 360 of the test rig and mock thermoelectric helical anchor. For simplicity, nuts and bolts in the acrylic box were ignored, and contacts were defined within a tolerance of 0.1 millimeters. Also, the energy from the heat lamps was applied evenly on all the exposed portions of the sand and mock anchor with nothing lost in the vacuum. This is a very ideal scenario, but these assumptions allowed us to focus on studying the behavior of the mock anchor. The thermal loads on the test rig were as follows. Full heat on exposed surfaces in the plane below the heat lamps. All of those exposed surfaces absorb heat via radiation with appropriate material emissivity and ambient temperature set at room temperature. The cooling system maintains room temperature and may remove unlimited heat to do so, creating a net zero heat in the test rig, and the exterior insulation of the box experiences convection with still room temperature air. All thermal conductivity values are either widely accepted from materials, such as copper or acrylic, or were provided by the manufacturer.
Due to experimental limitations, we were forced to make several trade-offs during the design process. One leading trade-off concerned the length of our radiator cylinders and the resulting cost to manufacture it. Long radiator cylinders correlate with increased heat dissipation for the cold side of the TEG because of 3 interconnected factors that relate to increasing depth: the increasing subsurface temperatures, the increasing thermal conductivity, and the increasing contact surface area between the radiator cylinders and the surrounding lunar regolith. However, we found that after a given point, further increases in the length of the radiator cylinders produced diminishing returns because of the mounting costs to manufacture longer and longer pieces. We compromised with an ending depth of 50 centimeters for the radiator cylinders, well below the stabilization region of subsurface regolith temperatures and well within the range of the 3 times the increase in thermal conductivity of lunar soil.
One key design trade-off was the complexity of the radiator cylinders versus build feasibility and keeping the design generalized. We went with a very generalized, just an outer cylinder and then a pipe in the middle. And we could have come up probably with a really complicated, optimized radiator cylinder design, but we also realized that our test was a proof of concept model, so we wanted to keep things as general as possible to provide something that had, some surface area more than just a regular cylinder, but prove the concept of, and something that real scientists could build on in the future. And also we had to choose a shape that we could feasibly actually build with our very limited metalworking tools.
The general process for creating the code for measuring the temperature was really not that difficult. Luckily for me, most of the hard work had already been done by people who wrote the libraries, so I only had to figure out how to use the libraries. Again, that wasn't really too hard, and I was able to work out most of the kinks relatively quickly. The first task I had to tackle was figuring out how to communicate between the Arduino and the computer I was using to gather the data and write it to the disk. The general process would be to first read each sensor off of the Arduino, then send the data through the serial port to the computer, then then on the computer I would read the data from the serial port and write it to the disk for later processing, of course. To do this, I used Python on the computer and the PySerial library, and just regular Arduino code combined with the libraries that I used to read the sensors on the Arduino. The biggest problem that I encountered was actually saving the data collected by the computer. On the first run of the experiment, I realized I was collecting the data wrong. This means that the way the writing to the files worked meant that to actually save the file to the disk, you first have to close the file, right? So you open the file, write the data to the file, then you close it, and on close it gets written to the disk. However, the way I was writing the program, the file never got closed. So what happened was I would open the file, read from the sensors a bunch, write to the file, and then the file would never get closed, and the data would never get written to the disk, and it was all lost. This happened on the first run of the experiment, and which means all of the data from the first run we got was completely unusable. However, for the second two runs, I realized this problem after realizing that all my data for the first experiment was gone, and I managed to fix it by periodically closing and then reopening the file to append to the end. To measure data for the voltages, all I did was hook up a series of resistors to the TEG modules and read the voltage from them periodically with a voltmeter. Just go down to the experiment and write the voltage down. To process the data, I used the programming language R. I just had to do graphs using the R library ggplot2, and all I had to do then was specify that I wanted to graph time versus each temperature value, and then combine those into a graph, and then combine the voltage into a graph and the wattage into a graph. And that worked reasonably well. So that's the process.
Our experimental study found that there did persist a significant temperature differential across the thermoelectric generator system through an applied heat source. For our project, we utilized results from two in-situ experiments with our testing rig, one of which was conducted with 500 watts of applied heat power, the other of which was conducted with 750 watts, and we also utilized results from 7 CAD model simulations, with applied heat ranging from 150 watts to 900 watts. These graphs describe the recorded temperatures over time for each of the two experiments. Over time, the temperatures on all parts of the system increased from the baseline ambient temperature levels until the point of stabilization, when all the various heat fluxes in the system became equal to each other, as indicated by the final temperatures in the graphs. We found that both the hot and cold side of the TEG increased in temperature throughout the experiment, but notably that the hot side increased with a much higher rate of growth than the cold side, demonstrating an increasing temperature differential over time. Also recording the voltage generated by the heat transfer across the TEG, as expected, we found an increasing graph that mirrored the changes in temperature differential. We also found, by comparing the two experiments and referring to our simulations, that overall an increase in input heat power correlated with an increase in open current voltage from the TEGs. Overall, our study proved the effectiveness of this helical anchor-based thermoelectric generator design, demonstrating its feasibility for use within the Artemis base camp, with easy installation, solid-state and low-maintenance functioning, as an integrated process of structural support with the device's modified helical anchor, heat dissipation capacity through its radiator cylinders, and power generation using its thermoelectric generators. However, the study itself was only half of the project. The heart of this research comes from the effort of the various members that made up the team behind the Artemis generation. Hi, my name is Ellie Montgomery, the team lead for Montgomery College's Artemis generation.
I'm Matthew Luden, an engineering major.
Hi, my name is Marco Lopterich, and I am a student at Montgomery College, majoring in aerospace engineering.
Hi, my name is Teresa Doley, and I will be completing my AS in Environmental Science and Policy this spring semester.
Hello, I'm Alex Gutierrez. I'm working with the NASA Mines Montgomery College Artemis Generation Group.
My name is Brian Sanchez. I am a mechanical engineering student at Montgomery College.
Hi, I'm Ryan Phillip, and I'm a mechanical engineer.
Hello, my name is Kane Timlin, and I am a computer engineer at Montgomery College, Rockville. But I am also a member of the Artemis Generation NASA Mines team.
I just wanted to spill some of my thoughts here real quick. I wanted to say it was a great learning experience for all of us. I think I could speak for all of us when I say it was a great learning experience.
I came into this program with no engineering background. I've always been more into the life sciences, such as biology. I never really considered a career in engineering before this experience.
I joined this project because I wanted something similar to my high school robotics program to do.
I joined the program in the first place due to various reasons, such as gaining the experience in terms of meeting and working with other people on projects.
To gain hands-on experience and learn more about the engineering world while working with a team to find a solution for real-world problems by using engineering.
To seek like-minded individuals.
I initially joined the program because I wanted to work on physics and engineering-based research and to figure out what it meant to be a real-life researcher. I definitely got a lot more out of this program than just science. Behind the scenes, I also handled the administrative and logistical aspects of the team, in addition to managing the project. I didn't expect that to be as rigorous and demanding as it was, but, well, it was, and so that's just something I had to learn through trial by fire.
This experience has honestly been like none I've ever had before. I had previously participated in official neuroscience research at Walter Reed Army Institute of Research, but that experience did not come close to this whole NASA Mines experience.
I learned a lot about some fundamental physical laws and fun facts about space that I didn't know before.
I wanted to really get in there with other people and do some engineering, do some building, do some actual programming that could be applicable to the real world. And I definitely got that. I got a really good experience with a lot of really good people, and I had lots of fun.
I learned how to think like an engineer and solve problems like an engineer. I learned the hard way that researching and completing engineering projects is completely different than conducting neuroscience research.
I learned a lot about thermodynamics and the moon, and I learned a lot about working with other people and actually building things.
A big challenge that we came across was figuring out how to set up the experimental portion of our research, because of the pandemic, we couldn't just fit our entire team into a workshop, and we didn't have access to the Montgomery College labs for our work, so we had to get pretty creative with how we set this up.
Some challenges that we also faced were re-strategizing how we were approaching the build process.
A couple challenges that we came across were definitely being able to construct the box in time. We were really crunching on that. There was a lot of things we did wrong. There was a lot of things that we could have done better. And there was a lot of fixing our own mistakes. And it became kind of a saying that most of the engineering we did was engineering to fix the mistakes that we made. And I think that's very apt because we made lots of mistakes. I'll come right out there and say that. We made lots of mistakes. We also had some troubles with the data collection software. That was entirely my fault. But we got them sorted out eventually, and we ended up, I think, with a pretty good run in the end.
Some things I would have done differently if I had the chance to do this program over again was, in the beginning, be more active in the research portion, along with understanding more math, physics, and thermodynamics.
If I were to do things differently or do the program again, I would definitely enhance my math and science skills.
Some things that I would like to do differently if I did the program over again is honestly maybe do something that didn't involve thermodynamics. Thermodynamics just kind of hurts inside to deal with, and the physics of it was definitely very wacky and to understand and deal with. I'm glad we were able to work it out though, and with the way that it went as it is, I wouldn't change anything personally.
And I gotta say, this program did help bring some sort of high spirit into my life. Everybody's going through something similar right now. Everybody's isolated and whatnot. It just gave me a little something extra to look forward to on a weekly basis.
And really, this NASA Minds project was a lot of fun. It was really a test of, logistical CAD and simulations, and I learned a lot about technical writing and practical engineering. The modeling wasn't too hard. Nothing we designed was that complex to model, but I've never done a CAD model with hundreds of parts. And just logistically with the practical engineering of making sure the nuts and bolts fit and everything, it has adapters and is in spec. I've never worked on a project this complex before. It was a lot of fun.
The most enjoyable part for me was actually building our project that we were working on in person. I thought that was pretty cool.
It was a great opportunity for students to be able to transfer their theoretical concepts that they're learning in the classroom into something that's tangible, into reality. And it really provides that wow factor that, man, this is what we're learning is legit and it can actually be done. It's a perspective shift.
I think what I enjoyed was researching. I felt like I was really working with NASA, going on NASA documents.
The best part of the program for me personally was just seeing the experiments take place. I didn't do the build portion of it myself, but I was there when we performed the first trial run of the experiment, and just seeing our test rig and our device in all its glory, and seeing it glow up and display our data in the computer, that was just amazing.
It really came together at the end. When our data came in and it matched the simulations, that was a special moment.
I am extremely grateful to have had this opportunity to get outside my comfort zone. This experience has just encouraged me to explore engineering for sustainable development, and I really hope to continue working on projects such as this that explore clean, renewable energy.
Connecting with everyone and working together was a great experience. I want to thank NASA Minds and Montgomery College for this amazing opportunity, and my team for everything we have done, and I cannot wait to do more in the engineering world.
I want to thank the Build team so much. I want to thank the Montgomery College for giving me this opportunity, and I want to thank Dr. K. I want to thank Dr. K. He got me a part of this team, so I appreciate him.
Thank you to everyone who helped put this together. Thank you to the MC people, the Montgomery College people, for putting this all together. Thank you to the NASA people for doing this. Thank you, Ellie, for leading the whole team. You've been a great leader.
I was extremely honored to work under Ellie, the team leader. She worked so hard on this project and was so encouraging of all members. She personally really helped me understand the project when I was completely lost on the real engineering content.
Thank you to all the staff at Montgomery College who helped out with this program and actually brought this to our attention and made this possible. And also a big thanks to the higher ups at Montgomery College who provided funding for this project, extra funding on top of what NASA gave us.
I would like very much to thank the admins from NASA and MC who worked with me behind the scenes. This project would definitely not have been able to come to life without them. I would also like to thank the NASA Minds folks, the MC program director, Dr. K, as well as our faculty mentor, Professor Thai, for making all of this possible. And I'd also really like to thank my team for all the hard work that they put into this project with me.
Thank you.
Thank you to all you guys.
Thanks, everybody.
Thank you.
Thank you.
Thank you.
We all worked hard, we all learned a lot, so that's really what matters. And with that, I'll say I'm out. Thanks.
So yeah, thank you.